started now. For next week, we have no speaker because of the Fox deadline the next day. And what we were thinking is that we'll still have pizza and people can just show up and like sit and socialize and talk with each other rather than listening to anyone tell about their research. But this week we do have a speaker. Ellis will be telling us about broadcasting in noisy radio networks.
Thanks, Dama. Okay, so hi everybody. I'm Ellis. This is joint work with Karen Spencer-Hillel, who's at Technion, and then Bernard and Goran, who are both here at Carnegie Mellon, and also me, who is here at Carnegie Mellon. And this is what everybody looks like. So radio networks, what are those? I wanted to start by just sort of gesturing at like, where does this model come from, and why is this a thing that maybe somebody cared about at some point before it just became like a purely theoretical domain. So let's say you have some city, you plop down a bunch of radio towers, and each of these radio towers has some range of communication. So maybe everyone can talk to everyone except this one on the far left and this one on the far right are very far away, and they're sort of out of range of one another. Moreover, let's just kind of pretend that they're all talking over the same frequency. So you might ask yourself, what happens when they try to communicate with one another? So for instance, suppose that this cell tower at the bottom and the cell tower at the left have some packet that they want to transmit to everybody else. So this one on the left has this brown packet, and this one on the bottom has this pink packet. So what might happen if they, say, both go to transmit their packets at the same time? So they'll send it out over the same frequency to everybody who's in range of them. So maybe the cell tower on the far right is listening in. Nobody else is broadcasting him, so he gets his packet. He's happy. He heard the pink packet. But what happens to the ones who are actually doing the broadcasting? So the cell tower on the bottom here broadcasted out the pink packet, but it's using the same frequency that the cell tower on the left is using to broadcast out the brown packet. So it's going to be very hard for it to actually figure out what this cell tower on the left was trying to say to it. And symmetrically, the cell tower on the far left is going to have trouble actually discerning what the cell tower at the bottom was trying to say to it. So neither of those are going to be able to really make out what the other one was saying. And then lastly, you have the cell tower at the top. Two different cell towers are trying to communicate to it. So they're using the same frequency, and it's going to listen in on this frequency, and it's going to get some sort of garbled mix of what both of them were trying to say to it. And maybe it's not actually able to make out what either of them was trying to say to it. So in the end, even though they both tried to broadcast to all of their neighbors over this frequency, only one of them ended up hearing what the two cell towers said. So I'm going to formally share this up a little bit now. So the radio broadcast model, or the radio network model, is a model of communication that was meant to capture these sorts of interactions over wireless networks. So what does a radio network consist of? So you have some graph. It has n nodes. And communication is going to happen in synchronized rounds. So you have round 1, round 2, round 3, and so forth. And during any particular round, a node is either going to broadcast to all of its neighbors, and it'll broadcast the same packet to all of its neighbors, or a node can listen in and try and hear what one of its neighbors is saying. So for instance, you might be in round 1, and in round 1 you might have, say, this node on the far left deciding to broadcast some green packet, and all the other nodes decide to listen in. So then the question is when do I actually successfully get a packet from a neighbor? And so to sort of capture what I was just talking about with the cell towers, we're going to say that if you go and you broadcast out a packet, or if you're listening and you're trying to receive a packet, you only actually receive that packet if exactly one of your neighbors sends to you or broadcasts a packet. So say if 2 of your neighbors broadcast to you in any particular round, you're not going to be able to hear. If 3 of your neighbors broadcast to you, similarly, you're not going to be able to hear. If 0 of your neighbors broadcast to you, nobody's trying to say anything to you. Of course, you're not going to hear anything. And if exactly one of your neighbors broadcasts to you, you will actually be able to make out what that neighbor is trying to say. And just a minor technical detail, the size of these packets that they're broadcasting out, we're going to say are something like log n bits. So this green packet that we're pushing around is something like log n bits. So in this particular example in round 1, both this node on the bottom and the node at the top will successfully receive the packet. Yeah?
So if 2 or more are broadcasting, then will I get the same signal as when nobody's broadcasting, or will there be a signal that says there was interference? And so
yeah. So that's a good question. So that's something that's studied in the literature, and it's called collision detection. And if you have collision detection, so yeah, we call it a collision when multiple neighbors try to broadcast to you in the same round. And if you have collision detection, you can do certain things more efficiently than you might if you didn't. So, yeah, good question.
We do not assume that.
Yeah, we don't assume that in this work, though. Okay, so that's the radio network model. So what is there to say about the radio network model? So kind of the simplest problem that you might think about solving in the radio network model is just spreading a single message throughout the network. And I'll call this message broadcast. And then, you might want to generalize this to, say, k-message broadcast, so spreading k-messages throughout the network. And I'll talk about these in a bit more detail. I just want to give a quick overview of what I'm going to be talking about for the next few minutes. So it's not totally clear how you should measure efficiency of a solution with k-message broadcast. So that's kind of where this idea of throughput comes in, and I'll talk about that. And then lastly, I'm going to touch on sort of two paradigms of how you might actually solve spreading one message or k-messages throughout a network that I'll call routing and network coding. So I'll start with message broadcast. This is kind of the simplest problem you can think of solving when working with a radio network. So in message broadcast, you just have a radio network. You also have some node that you designate as the source node, say S here. And the source node is going to start with some packet or some message, we'll say, of size log n. And so notice that we're allowed to broadcast log n bits in any given round. The messages are also of size log n, so we can broadcast like a single message in a single round. So we say that the problem is solved once every node in our network has the one message we're trying to broadcast to everybody. And we measure the efficiency of our solution in terms of numbers of rounds that are spent broadcasting. So for instance, in this particularly easy example, in round one, maybe the source decides to broadcast, everyone else listens in, it sends out the message, these two nodes receive it successfully, and then in round two, this node at the bottom is going to decide to broadcast, everybody else decides to listen in, it sends it out, and now everybody has the message. So, you can solve this instance of message broadcast in just 2 rounds. That's message broadcast. I want to just touch on some prominent known results before anything we did in message broadcast. So first off, what are some lower bounds? What are the minimum number of rounds that we need to solve message broadcast? So these are some possibility results. So kind of a trivial result is you need to order the diameter of the network. So you can imagine if you have some path that defines your diameter, your source starts on, say, one end of that path, you're going to make at most progress of one node along that path in any given round, so it's going to take you order diameter time to actually spread it along that path. So a bit more technically involved, actually before I was born, no-go alone showed that there are certain bipartite networks that need something like log squared n rounds. So no matter how you might decide to broadcast, you end up needing log squared n rounds to spread a single message throughout your entire network. And this is a network of n nodes. So that's what's known in terms of impossibility results. On the flip side, there are sorts of possibility results. So again, back around the time of no-go alone, there's this algorithm called decay that takes something like d log n plus log squared n rounds. So I notice that this is almost optimal. We hit the log squared n of the no-go alone paper, and we almost get this optimal d. But we have this annoying log n term hanging out with our d that's not quite optimal up to these impossibility results. So more recently in 2006. In 2006, some people actually showed that you can come up with an algorithm that's optimal for single message broadcast. So we hit the optimal trivial d lower bound, and we also get the no-go alone log squared. So we're very happy. It seems like we understand everything that we need to maybe about single message broadcast. We have matching lower and upper bounds.
Ellis?
Yeah.
So you're assuming that you know the network?
Yeah. So I'm eliding a few details about how these algorithms actually work. So decay is sort of fully distributed in the sense that nodes don't need to know the entire network, whereas I'm calling it FastBC, fast broadcast, actually assumes that you know the entire topology beforehand. And you can learn the topology in a relatively efficient way. So when we move into k-message broadcast, when we're using lots of messages, that sort of gets amortized away in the end. But yeah, good question. You do know the topology for FastBC. You do not for decay. Okay. Yeah, so that's what's known for message broadcast. So again, fastBC is optimal up to these lower bounds. So this is, again, just the slide of message broadcast. So the next natural question is like, well, I'm not really interested in just spreading one message throughout my network. I probably want to spread K messages throughout my network. So what is the K message broadcast problem? Well, it's kind of exactly what you think it is. It's just the message broadcast problem, except now our source is going to start with K messages, and our problem is solved not once every node has the one message, it's solved once every node has the K messages. And again, you might like think, oh, well, I'll just measure like the efficiency of my solution in terms of the number of rounds. But then the question is like, well, what is K? Is K like, polynomial in n? Is it exponential in n? Because like, we're probably, the number of rounds that we use is going to have some dependency on the number of messages. So throughput is supposed to be an answer to sort of that ambiguity as like, how are we actually supposed to, what sort of K are we supposed to use? So in general, we sort of think of fixing a network once and then using it over and over again. Like maybe we like build this network that we're communicating over, and then we're just going to do message broadcast for like the lifetime of this network. So K is going to be very large as far as we care. And N with respect to K is going to be sort of fixed, right? Like we fix our network, and then we're just broadcasting messages over and over and over. So roughly what throughput is it's something like, given a graph that defines a network and a source node, throughput is something like the messages, the number of messages I'm able to send per round in the limit of the number of messages. So just a little bit more formally, we'll say like the throughput tau of G comma S is the limit as K goes to infinity of K over the minimum number of rounds to broadcast those K messages. So like if I give you 1 billion messages, your throughput will be something like 1 billion over the fastest that you could possibly spread 1 billion messages throughout your network. Yeah, what's up, Tom? S is your source node. Sorry. Yeah, so your throughput is actually going to depend on your source node. Like you might be able to place your source node in a very optimal position that makes it easy to spread messages, or it might be in a very like non-optimal spot that makes it hard to spread messages throughout your network. Any other questions? Okay.
So at each round you spread one message, right?
At each round you spread one message. No, well, so you don't necessarily have to spread a single message. Are you asking if you broadcast a single message? Yeah, so a single node can broadcast maybe a single message in a single round. It can do other stuff too, which I'll talk about. That's kind of like the routing versus network coding distinction. So you can imagine doing something smarter than just trying to broadcast the message to your neighbors. Yeah.
So does the source matter? Like up to how did the...
I want to say yes, just because in the literature, source is always wrapped up in the definition of throughput. I'd have to think about it a little bit more. Yeah.
Is it obvious that this limit always exists?
Yeah, so you can actually show that this limit exists.
Is it decreasing? Or increasing? Oh, probably increasing, right?
So you can show, well, I guess the way you show this limit exists is like you can show that like the sequence is subadditive, and then use like Piketty's subadditivity lemma. But yeah, don't worry about it, the limit exists. Okay, so that's throughput. That's maybe how we're going to measure the efficiency of our broadcasting K messages. So now I define these two problems, message broadcast, K message broadcast, and how we're going to measure efficiency. So yeah, I want to hit on sort of two paradigms of how we might actually solve these problems. So far when we've been talking about it, it seems like really what we're just saying is like when you broadcast, you just broadcast a message. So for instance, the source might go and broadcast the pink message, and then it might go and broadcast the yellow message. And I'm going to call this routing. So in routing, the only thing that a node ever sends is just one of the messages, one of the K messages that you're trying to spread throughout the network. So what else might you do? Well, you're allowed to send log n bits, and you're allowed to send kind of like any log n bits that you want. So this is what network coding tries to exploit, is it says, well, maybe I'm not going to just send one of my messages. Maybe I'll send some like arbitrary combination of my messages, and I'll like ship that out to other nodes, and then maybe they'll be able to like recombine all of these arbitrary combinations of my messages in intelligent ways that'll allow me to do stuff more efficiently than routing. So for instance, maybe rather than sending like the yellow and the pink message, I'll send the mixed yellow-pink message as one packet and send that out. And then maybe hopefully both of these nodes will be able to like deconstruct the original messages that I combined into these two messages. So that's very abstract. What I want to do now is just talk about a little toy example to show like why you should think that network coding ought to actually be helpful in terms of number of rounds that you need to broadcast. So Okay, let's say we have a network that looks kind of like this. We have some message in the top left, we have some message in the top right, M1 and M2, and these are different messages. And so let's think about like how efficiently can routing do this? Well, so M1 needs to eventually get over to these nodes on the right, and M2 needs to eventually get over to these nodes on the left. So in your first 2 rounds, it doesn't really make sense for you to do anything than broadcast M1 out if you're doing routing, and then broadcast M2 out if you're doing routing. Okay? So then what can we do? Well, this message in the middle has both M1 and M2, and M2 needs to get over here, and M1 needs to get over there. So, in our next round, we're just going to ship out M1 to everyone, then those nodes on the right got it, and then the next round we'll ship out M2 to everyone. And now those nodes on the left got it. So in total, we use something like 4 rounds if we're doing routing. So how could you possibly do better than this? Well, let's see what network coding can do. So again, it doesn't really make sense for you to do anything than spend the first 2 rounds just shipping out M1 and then shipping out M2. But now we're allowed to use arbitrary combinations of our messages, right? So let's say this node in the middle is like, well, I have M1 and M2, and every other node has at least one of these. So I'm just going to compute the bitwise XOR of both of these. And I'm going to send this out to all the nodes in the network. That'll only cost me 1 round. And now all of the nodes either have one of the messages and they have the XOR of the 2 messages. So clearly they can recompute the message that they don't have from this. So all in all, network coding will only take 3 rounds to solve this. So we're able to save ourselves a round by sending arbitrary combinations of messages instead of just the messages themselves. So, any questions? No. Okay, cool. So neat. Network coding seems helpful. And this seemed actually to be supported by the literature. So for a very long time, if you just use routing, the best throughput that we could get was something like 1 over log squared n. And the way you should read this is if I want to send k messages, I can get away with using k log squared n rounds in the limit as k starts to dominate things. So cool. That's about as efficient as routing is. Network coding was, I guess, in 2014 shown to be quite more efficient by log and gap. So if network coding wants to send k messages, it can get away with something like k log n rounds. So cool. Maybe we have this log and gap. We can formalize our intuition that network coding is actually helpful and move from these toy examples to actually a formal proof that network coding is helpful in radio broadcast. But alas, it was not meant to be. So I guess Noga alone, so other people came along in 2014 and showed actually routing can be really efficient in terms of throughput. Rather than sending k messages in k log squared n rounds, you can get away with sending k messages in log n rounds, k log n rounds, which is just as efficient as network coding. So we lost our gap. We're very sad. Where did all of our intuitions go? And why are these toy examples not actually meaningful? So, okay. So I'm going to move into our work now. But just to reiterate what we talked about, we hit on kind of the simplest problem you can think of solving, which is message broadcast in the radio network model. And prominent algorithms that we talked about there were decay, which is this old algorithm that's almost optimal to this annoying log n hanging out with the d, and fastBC, which is optimal given the DE lower bound and the no-go alone log squared n lower bound. We generalized this to k-message broadcast. We talked about throughput as a way of measuring efficiency of k-message broadcast. And we also talked about these 2 paradigms of how you might solve these problems. And even though intuitively it seems like network coding ought to help, we weren't able to get a gap in terms of the throughput. Yeah. Yes. Yeah. So there is actually a log n impossibility, 1 over log n impossibility result. And I'm actually going to draw on that later. But, yeah.
So are there any assumptions on graph topology in this?
No. So maybe things are known for planar graphs. Are things known for planar graphs? I'm not totally sure. Yeah, but none of this stuff assumes anything about your graph topology, at least. So, okay. So this is where our work comes in. So we're going to fidget with the model a little bit. And we're going to just sort of add a little bit of random noise in 2 forms. So we're going to add either sender faults or what we call receiver faults. So again, the model's going to be the same, except we just have a little bit of random noise in the form of these faults. So what's a sender fault? Well, it's kind of like what it would sound like. So we see that sender faults occur if when you go to broadcast a message, so let's say this node goes to broadcast a message, with some constant probability, say a half, it just gets dropped from everybody. So like the sender fails with constant probability. And then maybe you have to go again and send it, and then it gets through to everybody. So that's sender faults. Receiver faults are, again, kind of exactly what you think they'd be. Now, independently at each of your receivers, if you send to them, the message gets dropped with constant probability. So maybe you go out to broadcast, it gets dropped from these two middle nodes, you're kind of annoyed, and you're like, oh, I really wanted that message to get through, and you go to broadcast again, and then it gets dropped, and then you got to broadcast again. So this is already actually kind of hinting at the fact that maybe receiver faults are more difficult than sender faults, in some sense. But yeah, so that's sender and receiver faults. And now when we're talking about k-message broadcast, this is just the slide from before. Yeah, what's up?
So does the sender get feedback to like?
That's a great question, and I'll address that in a little bit. Yeah, you all are asking all the right questions. So, okay, k-message broadcast, right, now things have to occur with high probability. So now we're going to say the problem is solved once everybody has all k messages with, let's just define high probability as something like 1 minus 1 over k. You can define this in terms of expectation. It doesn't really change anything about our results. So, okay. So we fidgeted with the model a little bit. We have these faults now. Who cares? Well, for one thing, this model is a bit more realistic. So, in particular, the original radio broadcast model assumes that, like, if I send a message without any collisions, that message is going to get through no matter what. And this is like a pretty strong assumption to make if you have things like environmental noise or hardware failures, other things that might interfere with communicating your message. So, if it turned out that we had all these possibility results, like decay and fastBC, that were really just like exploiting this assumption in our model and just like using the fact that they guaranteed message delivery provided no collisions occurred, we probably wouldn't be very happy. And these would not be algorithms that we cared about in practice. On the other side, we saw that like we weren't able to get this login gap, even though we felt that we ought to be able to get this login gap. So maybe if we tweak our model in a little way like this, by just adding a little bit of random noise, all of a sudden we'll show that like network coding is actually instrumental to achieving good throughput. So, okay. So what do we actually show? So I'm just going to give like a high level of what our results are here now. So these, again, are just the runtimes of decay and fastBC with single message broadcast. And the first question you might naturally ask is like, well, how do these fare if I do just introduce a little bit of random noise? So if I introduce, say, just sender or receiver faults, what happens to the runtime of these algorithms? So kind of nicely, nothing for decay. So decay is actually like robust as is to sender or receiver faults. So that's nice, and you might think, okay, great. Well, I hope fastBC is too, because that was optimal. And I'd like to just have an algorithm that's still optimal in the faultless case, because my lower bounds are going to carry over to the faultless case. So unfortunately, that's not true. If you introduce just a little bit of sender-receiver faults, fastBC, like as it is, picks up an extra log n on the D, which is kind of just the same runtime as decay. So that's sad. We're sad. So the next thing we do is we provide an algorithm that's able to get rid of this log n and be optimal up to this linear diameter term, or it's optimal on this linear diameter term, and it's totally optimal except for this like extra log n that we pick up on the log squared n. Okay, so that's nice. We might also be interested in like, well, what can we do in terms of k-message broadcast in the faulty setting? So we also show how you can take decay and then use network coding to I wanted to preface this with something first, actually. So you're trying to generalize to k-message broadcast. So kind of the naivest thing you could think of doing is like, well, if I have k-messages and I can send one message in d log n plus log squared n rounds, I'll just repeat that k times. So the stupid thing you could do is like pick up an extra k here and an extra k there. And so, okay, that's kind of our baseline of trivial. If you kind of intelligently use network coding, these network codes called random linear network codes, you can actually push the k to just a log n term. So now like your d log n and your log squared n don't have this k that you were picking up if you did things in the trivial way. Similarly, you can do the same thing for this new version of fastBC. So again, we're like picking up a log n term, or here we're picking up a k on the log n log n term, but like our other terms are free of like new k's. So those are the possibility results. But what I really wanted to talk today about was what I wanted to talk about today was the impossibility results. So what are those? So I think coolest and most interesting to me is like we're actually able to get log n gap if we have receiver faults. So again, this is like every receiver drops the message with constant probability. So yay, we're able to recover our gap. That's nice. It shows that like network coding is actually helpful. Maybe not helpful if you assume guaranteed message delivery, but like it allows you to be robust to things like receiver faults, whereas you can't do that if you're using routing. So asymmetrically, maybe surprisingly, there's no gap with sender faults. So there's, routing and network coding still have the same performance in terms of throughput if you have sender faults. And the way that we show that is you can take any algorithm from the faultless setting that assumes, and it's assuming no faults, and you can transform it in a way that makes it robust to sender faults. So if we didn't have a gap in the faultless setting, and we're able to preserve throughput with these transformations to the faulty setting, like we're going to inherit that like lack of a gap. So, any questions? Yeah.
The previous slide, do you need network coding for your throughput results?
Which throughput results
The
here?
last two.
Oh, okay.
Can you do those things without network coding?
We did not.
What's known actually about that without network coding, without faults even?
So you can get a throughput of 1 over log n with both routing and network coding. Yeah. Yeah. Okay. Any other questions? No. Okay. So yeah, I wanted to like maybe not prove in full detail, but at least strongly gesture at the proofs of how we actually recover our gap. I'm probably not going to have time to get to the O log n part, but at least get to the omega log n part, which is kind of the more interesting part of the gap because it shows that like these things are separated at least this far. So yeah, I'm going to be talking about the omega log n. So okay, just so we're on the same page, like I've been talking about like the gap, but I haven't really like formally defined what I actually mean when I'm talking about the network coding gap. So let's do that. Let's define that. Let's just define the throughput on some topology with some source node. If you use routing as like tau superscript r of g comma s, and then symmetrically you can define it for network coding as tau superscript nc of g comma s. So the network coding gap is really quantifying like the difference in worst case performance between these two things. So what we're going to do is we're going to look at like the worst case throughput of any like network with some source of network coding and compare that to the worst case performance of routing over all possible choices of networks and source nodes. So that's what the gap actually is. And our gap is actually going to be particularly strong. So this comes back to Nick's question where he asked, well, can you see faults when they occur? So we're going to sort of beef up routing. We're going to be like, routing, you can have the following superpower. You're allowed to know where and whenever a fault occurs. And even despite having the ability to like know when faults occur, which network coding is not going to have, we're still going to be able to get this log n separation between the two. So, yeah.
So what can you say about the minimum of the ratio rather than the ratio of the minimum?
Yeah, so well, I guess really what you're interested in is the max of the ratio. Like you're looking at like the maximum gap. So like that's like if I fixed a topology, then or like if I was searching over all topologies and I was comparing network coding to routing, like give me the topology where like network coding beats routing by the most. And yeah, I'm not going to talk about that today, but we actually like do that in the work. By just kind of like messing with maxes and mins, you can show that that is. I'm going to flip this. That is an upper bound for this. So you can kind of like, if you're able to show this, you get a trivial bound on that. it would be easier if I like wrote things down, I guess. But they're related, I guess, and it's easier to show stuff for that, and we can actually show stronger gaps on that. So we show like a log squared and bound on a particular topology for that. But I guess most of what's been talked about before quantifies more like worst case performance to worst case performance rather than fix a topology and like what's the gap on that topology. But yeah, great question. Okay, so routing's going to have this superpower. It can see whenever faults happen. So how are we going to actually prove this omega log and gap if we have receiver faults? So at a very high level, what we're going to do is we're going to argue that the star topology, which I'll define in a few seconds, is very hard for routing. Well, sorry, actually, before I get to that, how do we show this in general? Well, we have to show that there's some topology that's very difficult for routing. So this will give us, don't worry too much about O versus omega, but this will give us like the right bound for the denominator. And then we have to show that, in general, network coding always achieves a good throughput. So this will give us the bound for the numerator. And like we had this in the faultless setting. Remember 1 over log n for network coding, but it's not totally obvious that we have it in the receiver fault setting. So if we combine both of these and we take the ratio, we'll get like our coveted omega log n gap. So, okay, I'm going to start with the impossibility result for routing, because that's really the more interesting thing here. So we want to come up with a topology that's very difficult for routing in terms of throughput. How are you going to do that? Well, at a very high level, we're going to argue that a star topology is hard for routing. And then we're just going to embed a bunch of these star topologies in a network that's already very difficult for routing. And like the confluence of these two difficulties is hopefully going to make the best throughput of routing not all that great on this network. So the first thing we have to do is argue then that star topologies are hard for routing. So again, remember that like routing is allowed to see, we're beefing up routing. Routing is allowed to see whenever faults occur, receiver faults in this case. So without loss of generality, you can kind of think of like the best routing scheme. Oh, sorry, there are end nodes here. But without loss of generality, what's like the best thing that routing can do? Well, it's probably just going to like pick a message and then just send that over and over again until it knows that all of the receivers have that message. And then it'll go to the next message, and it'll send it over and over again. So maybe you're reordering the or you like didn't actually send them in this order, but like you can sort of just reorder the order in which you send messages, and it's fine. So without loss of generality, we're just picking a message, sending it till everyone has it, going on to the next message, sending it till everyone has it. So, so we want to show that the star is hard for routing. So we're going to show that you need, like, to send k messages, you need at least like order k log n rounds. Okay? So let's just like assume for the sake of contradiction that we can get away with like a small fraction of that. Like we need like k log n over 4 rounds to send all these messages. And again, we're like in this random. We have a little bit of random noise, so we have to like succeed with high probability. We don't need it to actually like properly always succeed. Okay, so what do we know? So every message is going to be sent on average like log n over 4 times. So just by like Markov's inequality, we know that there are a whole bunch of messages that are not sent that many times. So like at least half of our messages, at least k over 2 messages, aren't sent more than like log n over 8 times. So we have a bunch of messages, and we're able to like get through, like broadcast them to everybody without actually sending each one too many times. So okay, maybe that's not an issue, but it will turn out to be an issue. So if you think about like what is like how long do I actually expect each message to take? Well, like half of the receivers each time I send a message don't actually receive it. So if I send a message, it'll get through to half of the people that don't have it, and I'll keep doing that. So I'll get through to half, and then I'll get through to half that don't have it, and half that don't have it. So like we expect that we require something like log n rounds to actually get our message through to all of our receivers. So what does this mean? Well, we have a large fraction of our messages, at least half of them, use like less than an eighth of their expectation. So this seems like pretty unlikely. And if you set up the turn-off bound right, you can actually show that like the probability that so many messages are able to use such a small fraction of their expectation is going to be exponentially small in n. So that'll give us a contradiction. Like with very low probability, can you actually get away with sending lots of messages just a few times but like we're supposed to be succeeding with very high probability. So supposedly we're able to do this with very high probability. So what does this mean? Well, k log n over 4 rounds isn't sufficient to send k messages on a star, so we need at least like omega k log n rounds to send k messages on a star. So any questions? Yeah, okay, cool. Okay, so let's like put that in our back pocket. Stars are hard for routing. What's the next thing we're gonna do? Well, like I said before, we wanna take stars and we just wanna embed a bunch of them on a network that's already really hard. Like, this alone doesn't give us our routing impossibility result. This would say like, you wanna send k messages, you need k log n rounds, it'll be like 1 over log n. Your throughput for routing would be like 1 over log n if you just tried to use a star. So, I forget who asked this. Somebody asked about like throughput impossibility results. So a paper by Mohsen Ghaffari and Bernard and some other people showed that the best that you can hope for with throughput is something like 1 over log n. And the way that they showed this is like by providing a network, or by demonstrating that a network exists by the probabilistic method. So what does this network look like? Well, it has some source. It's got to have a source. That source is just going to be connected to a bunch of quote-unquote sender nodes, say like root n. And each of those sender nodes is going to be connected to a bunch of receiver nodes, again, about root n. So yeah, I drew these dashed because these are like edges that are shown to exist by the probabilistic method, but it's not actually constructive. So why is this actually like a hard network? Well, they show by the probabilistic method that like at most a 1 over log n fraction of any of these receiver nodes in any given round receive a message. So like no matter which subset of sender nodes you pick, you're only going to be able to successfully, without collision, get a message through to like a small fraction, a 1 over log n fraction of your receiver nodes. Any questions on that?
Is the graph random? What's the graph in the middle?
So it's a randomized graph that exists with like non-zero probability. So, okay, so like if I wanted to say send one message through this graph, I would need at least log n rounds because I only get through to like 1 over log n of them in any given round. So, okay, what are we going to do? Well, I said we're going to embed a bunch of stars on this graph. Where are we going to embed these stars? Well, we're going to kind of like take each of our receiver nodes and effectively turn each of those into a star. So I colored these just to like help your eye follow what's going on. But we take each of those and we're going to duplicate them a bunch of times. So we're going to take this yellow node, it's going to turn into a bunch of identical nodes. This orange node, it's going to turn into a bunch of identical nodes and so forth. So that'll look like that. Fancy animation. Okay, so now we don't have like about root n receivers, we like have all these clusters. So we have like root n clusters. And I contend that like the same thing holds for clusters that held for the original nodes. So in particular, I'm going to argue that like a 1 over log n fraction of all of your clusters receive a message without collision in any given round. Why is that the case? Well, notice that like any node in a cluster is connected exactly like the node that it was derived from was connected, right? And we have the same number of clusters that we had nodes originally in like this network. So, moreover, I guess, if I'm able to send a message by picking some subset of sender nodes, if I'm able to get a message through to a receiver node in the original network, then it gets through to all of the same nodes in that cluster. And every node in a cluster, if one node in a cluster gets sent a message without collision, then all of the nodes in the cluster will be sent a message without collision, because they're all just connected identically to the sender nodes. So again, we're still able to say that like a small fraction of all of our clusters are actually sent a message without collision. Any questions? No. Okay. So, okay. Well, I promised you all that I was going to embed a bunch of stars in here, and it doesn't look like I've like quite done that. Like this kind of looks like a star, right? There's like a source, and it's connected to all these ones, and this kind of looks like a star, like there's a source and it's connected to all these ones. But like the node from which this cluster was derived was like connected to 2 nodes. Now every single one of these is connected to 2 nodes, and that doesn't really seem like a star. But without loss of generality, you can actually kind of think of each of these as a star. Why is that? Well, Each of these nodes, well, every node in a cluster in any given round they're all either sent a message without collision or none of them are sent a message without collision. And that's really like the only property about stars that we cared about from the get-go anyway. So yeah, effectively each of these is a star. How big are each of these stars? Well, we had like root n senders, root n clusters. If we want to like stay within the bound of order n nodes, we can like make each of them of size like about root n. So okay, we have like root n stars of size root n. So by this thing we put in our back pocket earlier that like stars are hard, each cluster, if it wants to succeed with high probability, is going to need to be sent a message without collision a lot of times, because each of them is just sort of like a star. So each of them is a star of size root n. Stars require, a star of size n requires k log n rounds. So each of these is going to need like k log root n rounds. So it's going to need like k log n rounds. So okay, now we can actually just sort of conclude what we wanted to by combining these two facts. So if I wanted to hit every star once, I would need to use like log n rounds, because only a 1 over log n fraction of them receives a message in a given round. But if I want each of my stars to receive all k messages and succeed with high probability, I need to like send them broadcast to them without collision at least like k log n times. So in total I'm going to need like k log squared n rounds to hit all of my stars as many times as they need to be sent a message. So what does this tell us? Well, remember what throughput is. It's just like k over like the most efficient that you can send k messages as k gets very large. And we said, well, the most efficient you can send k messages isn't going to be like k log squared n. So it's going to be like k over k log squared n. And so we can conclude our 1 over log squared n throughput bound. So sweet. That's like we want to show this omega log n gap. We just showed this top bit. We need to show the omega. The top bit's actually the more interesting part for this proof. This bottom part's actually going to be extremely straightforward, given what I said earlier. We want to get a throughput of 1 over log n. Remember that I said like we were able to take decay, use network coding, and come up with an algorithm that sends k messages in something like d log n plus k log n plus log squared n rounds. Throughput is just like k over the minimum number of rounds you need to broadcast. Well, this is definitely an upper bound on the minimum number of rounds you need to broadcast, or maybe a lower bound. It's one of those, whatever it has to be. So what throughput does this algorithm demonstrate you can achieve on any topology? Well, like k over the number of rounds it requires, which is d log n plus k log n plus log squared n. As k goes to infinity, who really cares about these terms without k? And you end up with like 1 over log n. So cool. That shows our omega 1 over log n throughput bound. And those two things together, we argued, said, give us our omega log n gap. Yeah, so we're happy with that. And that's all the stuff I'm going to prove today. And I'm just going to like quickly summarize all the stuff I talked about now. We kind of tweak the model just a little bit, this radio network model. And after tweaking it, we're still able to provide efficient algorithms. So for single message broadcasts, we're able to show that decay, which is this old school algorithm from the faultless setting, stays robust. FastBC, which it was this optimal algorithm, picks up an extra log n on the D. That sucks. But robust FastBC, which is this algorithm that we come up with, can actually shave this log off of the D, and it's optimal up to this annoying log n hanging out with the log squared n. And it might actually be that our lower bounds from the faultless setting obviously carry over into the faulty setting, but maybe you can actually prove a stronger lower bound that shows that log squared n plus the lower bound from the faultless setting was log squared n. Maybe in the faulty setting you can prove a lower bound of log squared n log n. Maybe this is actually optimal. We don't know. So we also generalize these algorithms to k-message broadcasts. So you can use network coding to take decay and turn it into something that broadcasts efficiently with k-messages. And then you can use, again, network coding, random linear network codes to take robust fast BC and turn it into something that broadcasts efficiently. And then lastly, we just hit on some impossibility results. So, we lost our gap, or we thought and we hoped that we had this gap in the faultless setting. We didn't. As soon as we introduced receiver faults, we're actually able to recover it, and we get our log n gap. Today we just proved the omega, but this gap is actually, you can show it to be tight by showing that there are networks that are hard for network coding and that routing always does at least so well on any given network. And kind of interestingly and asymmetrically, we saw that sender faults are actually it really matters if you're using receiver faults or sender faults in terms of throughput in this gap. So like if you have sender faults, you can actually just transform algorithms from the faultless setting to algorithms that are robust to sender faults in a way that like preserves throughput. So since we didn't have a gap in the faultless setting, we end up with a gap. We end up with no gap in the sender fault setting. So thanks. That's all I have to talk about today.
All right, are there any questions? Okay, ask a question. Sorry.
Yeah.
So as somebody said a problem where given a network, come up with the best network of specific strategy to maximize throughput or minimize the number of rounders. So it's an optimization problem.
Or so how does that differ from what we're doing in your mind?
So then given a network, there should be some optimal strategy.
Some optimal.
Some optimal strategy.
Oh, okay.
Specific to the network.
Okay.
And you want to find this strategy.
Okay. How efficiently can we find the strategy? Is that what you're asking?
Yeah. Or how can you approximately find this strategy?
Yeah, I don't know that anyone studied this. Goran's shaking his hand, maybe.
I mean, there was some work like that, but it's a centralized problem, right? So that's not really what we are studying here, but there was some approximation algorithms, but in general it's pretty hard.
Get a login approximation.
Yeah.
Why is it a centralized problem if you know the, you said that you know the topology, right? So if you look at one specific graph and you already know the topology, why does that suddenly make it central?
Okay, yeah, right. You're right. If you know the topology, yeah, it's not centralized, then you can maybe do something better, but we just had an existential bound. Not optimal, not universally optimal for a graph, but existentially optimal for all graphs.
Yeah.
I was going to ask, so you always studied random errors. Has any, in this
Adversarial errors.
Yeah.
Yeah, so there's a, what is it called? There's a different model. It's called the, I don't remember what it's called. There is an adversarial model where an adversary gets to choose some subset of edges in each round and just be like, no messages get through those edges.
Oh, I see. So do your upper bound, for example, does your decay with RLNC still work on that model? Have you studied it?
I don't know. I haven't thought about it. I would guess no,
Yeah, okay.
but I don't know off the top of my head. Yeah.
So the biggest gap in the server is sender and receivers when is high degree.
Yeah, high degree nodes in general are pretty hard. Yeah, I think that'll make it pretty easy. I mean, then you can get away with.
Well, I guess the constant degree is easy.
Yeah. So if you bound the degree by a constant, then I think you ought to be able to get away with just maybe a constant overhead once you add faults, especially if you know when the faults occur.
Yeah, decay is actually d log delta log.
Yeah.
So for constant.
There you go.